How's it going, everybody? This is going to be another video in my little series, I guess, about this Quincy 325 compressor that I'm working on. This particular video will be about the wiring for the controls for this motor that I'm going to be using on the compressor. So the way this is going to work is I have this one 240 volt circuit coming down the wall here into this junction box where it splits off between my welder outlet and this blade disconnect. The way I have it set up, or the reason I have it set up this way, is so that I can definitively turn off the compressor when I'm using the welder. So since I couldn't run both of these on this one circuit, this is 8-gauge wire, I wouldn't be able to run both of them at the same time. I want to make sure that if I'm using the welder, I can shut off the compressor. Also, I believe it is a code requirement that if you are running something like this, you need to have a disconnect within sight if the breaker panel is not within sight of your installation. So that's another reason for having that. So I have power coming from this disconnect to my control box. And the control box obviously powers this motor, which is a 7.5 horsepower Balder motor, single phase, obviously. The 325 does not need a 7.5 horsepower motor, but this is what I was able to find for a reasonable price on Craigslist, so that's what I'm going to use. The pump itself will only draw up to 5 horsepower, so it's not like this is going to be running full tilt all the time. Now moving on to the control box. This is something that I assembled from essentially a pile of parts from a previous job that they were just going to throw away. So I obviously figured I had a use for them, so I took it home, and that's why this looks kind of cobbled together. But we'll go through this and explain how it's all wired. Hopefully help some guys out that are wiring a compressor. They're probably not going to do it this way because this is sort of unique, but the same principles apply. The contactor is wired essentially the same way, so hopefully it's helpful. The power from the disconnect, remember, comes up the side of the box here and enters the box. And just for orientation's sake, this is a contactor. This is a transformer. These are two 1 amp circuit breakers. These are contact blocks, so they essentially just allow you to connect wires together without wire nuts or something like that. It's much cleaner. These are indicator lamps. This is obviously a switch. And of course I have a pressure switch down here that is not currently plumbed into the tank, but it will be. And that is essentially all the components. As like a subcomponent, you might call it, right here on the bottom of the contactor. This is a thermal overload. All right, so we'll go through all this together. Also, there are two switches essentially on the side of the contactor that are actuated when the contactor turns on and off. All right, so contactor, that is what turns the motor on and off. It's essentially a large relay that exists solely for the purpose of turning the motor on and off. When you have a large motor like this that pulls a lot of current, especially on startup, I think the instantaneous startup current of the motor like this is like 160 amps or something like that. You can't pull that kind of power through a rinky-dink little switch like this. So you use a contactor. And since it is essentially a giant relay, the way that it works is you have low power that you switch on and off, and that low power circuitry actually actuates an electromagnet inside the contactor that turns it on and off. Okay, so the coil is what that's called. When you give power to the coil, it turns the contactor on, motor turns on. When you cut power to the coil, contactor turns off, motor turns off. Okay, so in this case, the low power that the coil requires is actually 120 volts. There are a lot of contactors that use 240, so you don't have to use a transformer to get 120 volts. But in this case, I didn't want to change out the coil. I already had the transformer from the parts pile, so that's what I used. Okay, if I wanted to use 120 without using a transformer, I think the only way that I could have reasonably done that is to have pulled a neutral conductor into my circuit here and used one of the two hot legs in the 240 circuit to make a 120, which is essentially how your house is wired if you live in the United States. But again, I'm using a transformer, all right? So I get 120 volts from the transformer. the transformer is wired in. See these two 14 gauge wires right here? Those are actually bonded inside the contactor terminal block here to the larger wires behind them. So these little 14 gauge wires are actually connected to these two larger wires. All right, so that's how they get power. Those two 14 gauge wires run to this circuit breaker and then out. So this circuit breaker protects everything downstream that's 120 volts. The 240 is obviously protected by the breaker in the main panel, but all this small wiring is protected by these little 1 amp circuit breakers. So we got 240, still it's 240 because it hasn't hit the transformer yet, going into 3 and 4. From 3 and 4, it goes out to this orange and black to the transformer. From the transformer, it goes to H1 and neutral. So these two contact blocks provide the start and end point, essentially, of the 120 volt circuit, okay? So H1, that's the hot. So the way this works is we have a wire right here coming from the hot contact block to this side of the coil. So now we have the hot going to the coil. The other side of the coil, this black wire right here, comes out to this switch, okay? From the switch, it comes back in to this set of contacts on the thermal overload, okay? See NC, that means normally closed. So normally, if this thermal overload is not tripped, those are closed and power flows through them. So this black wire right here is coming from the switch on the front panel, and then it comes out on this wire here, okay? This wire right here goes to 1. This contact block labeled 1, right next to number 2, okay? 1 goes out this 1/2-inch conduit to the pressure switch. From the pressure switch, it comes back into the box into number 2, okay? So 1 and 2 are literally just connected to the pressure switch. 2, you'll see this black wire right here, runs from 2 to the neutral, making a complete 120 volt circuit, all right? So coil to the switch, switch to the thermal overload to the pressure switch back to the neutral. And that's the whole 120 volt circuit, or the control circuit, I should say, that for turning the motor on and off. So what that means is if this switch is on, and if the thermal overload is not tripped, and if the pressure switch contacts are closed, meaning the tank is not up to full pressure, then the coil circuit is totally completed. The coil turns the contactor on and the motor starts. If any of those things are not met, meaning if the switch is not on, if the thermal overload is tripped, or if the pressure switch is open, meaning the tank is at full pressure, the coil does not actuate and the motor does not run. Okay, is that clear as mud? The purpose of the thermal overload, if it's not totally clear, is to shut power to the motor if the motor is pulling too much current. So if the motor is overloaded, say it's pulling too much load, or it's overloaded by whatever it's powering, or if it's getting too hot, it's going to start pulling more current. Once the current reaches the set point for a predetermined amount of time, this will actuate and cut power, or it'll open these two contacts, which has the effect of cutting power to the coil, which again will turn the motor off. Okay? So this is a requirement for a motor like this, of this size, in an application like this, okay? So you need that. If you have a motor starter that's just this, just the contactor with no thermal overload, you gotta get one if you're running a big old compressor like this. The only other components in this box, aside from the lights here, is this switch, and that's it. These two run the lights on the front, as does this set of normally open contacts on the thermal overload, okay? This switch here is normally closed. This switch here is normally open, meaning if the contactor is not actuated, this switch is closed, meaning power can flow through it, and this switch is open, meaning power does not flow through it. Similarly, these normally open contacts here, if the thermal overload is not tripped, these are open and no power flows through these wires. All this does is turn these lights on and off. So the normally closed switch here goes to the green light. So since normally, if the contactor is not actuated, that switch is closed, that means this light is on. The normally open runs to the red, meaning that light is off. Unless the contactor is actuated, then it switches, okay? Closed goes to open, open goes to closed. The green light turns off, the red light turns on. This little switch here, this set of contacts, goes to the yellow light, meaning that when the thermal overload trips, or if, hopefully it doesn't, if that trips, this normally open set closes and this yellow light turns on. Now remember, if this trips, it cuts power to the coil, which shuts the contactor off, which shuts the motor off. So if this thermal overload switches, the yellow light will turn on, the red light will turn off because the motor is off, and the green light will stay illuminated, indicating that you have power to the box, but the compressor is not running. So the motor turns off and you're like, what the heck, did the power go out? No, you still have green, and the yellow tells you that the reason that it's not running is because of thermal overload. All right, so let's go ahead and power this up. We got green light on the box there. And since the pressure switch, go back there. Since the pressure switch is not plumbed into anything, if we turn this switch on, motor's definitely not overloaded. It'll turn on, okay? Now, the thermal overload, you can trip it manually here to test it. Oh, didn't trip it all the way. You gotta turn it all the way here. Like that. See? Power to the box, but thermal overload is tripped. That's why it's not on. You can reset it. Whole thing turns on. Switch it off. And so you still got power. So if we shut this off, power to the box is now cut. There's no hot power anywhere in this box, which is why it's safe for me to jam my finger around in there. Okay, clear as mud. Hopefully that helps you guys understand this a little bit better. I've made this video a couple times trying to make it, trying to be, oh my God, I can't even do it now. Trying to make it exude brevity, we'll put it that way. But as you can tell, that's not something I'm very good at. But hopefully that helps you understand all this that's going on in here. If you're just wiring up a regular old magnetic contactor or magnetic motor starter, you're not gonna need to know anything about the transformer or any of that stuff. It's just gonna be this, and that's pretty much it. But the principles are the same. This is just a regular magnetic motor starter with extra goodies that I wanted to put on there because it makes me feel like this is a industrial compressor, which it is, but it's in my garage, so why not? All right, hopefully you guys enjoyed that. Hopefully you're not asleep, or if you were trying to go to sleep, it's an ASMR kind of thing, I hope you're asleep. So, thanks for watching. Catch you on the next one.